Okay, so today we're going to talk about how discoveries have been made about space and the universe through using different kinds of technology. We're going to start with very primitive, like very old technology, and then we're going to move to more modern times as well as what we know about our universe as of now. So again, like I said, we're going to quickly look at various technologies people have used throughout history to make astronomical discoveries. We'll also learn about two very large distance units that are commonly used in astronomy. You're going to notice that in astronomy, we don't use kilometers as often. Kilometers are great for distances on Earth, but not so much, of course, in space. The two units we're going to look at are something called the astronomical unit, and then something else that I'm pretty sure you have heard of before called the light year. Anyway, then we'll have some time for practice. We won't have to really worry about that so much today. I'll give you some time tomorrow to get that stuff done. Let's get going. So first of all, sundials. This is the earliest form of astronomy technology, if we can even call it that, that we'll talk about. Sundials originated in Egypt around the year 1500 BC. That's almost like 4,000 years ago now. They were, of course, just an ancient way of telling the time of day. This was before watches or anything. So they were a way of kind of monitoring what time of day it was. Cultures have made use of the motion of the sun in the sky as a means of telling time for thousands of years. So a sundial was just a technology that kind of formalized it. We've always known kind of where the sun is in the sky, tells us what time of day it is, of course, but sundials were kind of a cool way of tracking that. There was something else also invented in Egypt. They called it the quadrant. The quadrant was basically just like a 90-degree angle with a movable little stick thing here. It was used to measure a star's height above the horizon. We call this the altitude of an object. We'll get into that another time. So for example, a star sighted through a quadrant might have a height of 35 degrees. So they measured just how high in the sky it was relative to the horizon. Something else called the astrolabe that was invented kind of around the same time, maybe about 100 years earlier, I guess, in Greece. It was used not only to find the height of stars, but it was also used to find something called the azimuth, which is basically an angle version of compass directions. If we were still in school right now, we'd actually be making our own little astrolabe. You can actually make one out of a paper plate. And it's kind of cool because then you can kind of use it to tell where, like relative to the north, an object is in the sky. But then there's also this other movable piece here, like imagine this little fan blade kind of thing moving. It also can be used to tell like how high up the object is. So just in terms of the azimuth measurement, again, that's just kind of relative to north. How they've defined it, it was entirely arbitrary, but they defined it as 0 degrees being pure north, 90 degrees as being east, 180 degrees as being due south, 270 as being due west, and then other angles, of course, in between. So the astrolabe was basically the same thing as that quadrant from the last slide, but just with an additional measure of its azimuth, right? Another one was called the cross staff. This was quite a bit later. It was mostly just used to find the angles between two different objects in the sky. So it had this sliding piece right here as forming like the T part of the cross. You could slide it closer or further away. Of course, if it was further away, you'd have like a smaller angle in there between the two objects. And then there were like little notches on here that you could read to tell you what the distance was between those objects in the sky. So if you wanted to find between two stars, you'd use a cross staff for that. And again, that originated in France. Not that you need to know that or anything, just an FYI. All right, now for the big boy, right? This is the one we all really care about here. The telescope. This originated in the Netherlands around the year 1600 AD. That might sound like a long time ago, which I mean, yeah, 400 years ago, sure. But it is a relatively new piece of technology that totally changed everything for us, of course. The telescope, needless to say, allows a greatly zoomed in look at objects in the sky. You can actually see things closer up, right? Totally changed astronomy, completely changed everything we knew about the sky. And it was mostly thanks to this guy right here, Galileo Galilei. He's from Italy, I believe. Oh yeah, there it is, says right there. Italian astronomy, Galileo was the first major astronomer to make excellent use of the telescope. The telescope, as far as I'm aware, I could be mistaken on this, I don't believe it was actually originally developed as an astronomy tool. It was just Galileo who said, hey, you know what? This could actually have some use to it, you know? So he was the first person to ever see the rings of Saturn. He pointed his telescope that he had at Saturn and he went, oh, wow, that's not just a star in the sky. There's actually something else to it. It's pretty phenomenal, right? Now, his observations provided proof for Copernicus's heliocentric model. We talked about that in class before as well. Remember, heliocentric, break that word down, heliocentric. Heliocentric means the sun at the center of our solar system. I know this is a bit of a throwback from a previous lesson, but remember early on, for well over 1,000 years, people believed that the Earth was the center of our solar system. The heliocentric model proposed by Copernicus said otherwise. It said the sun was at the center and all the planets were going around the sun. His observations, his direct observations through telescopes helped reinforce that. All right, now, astronomical unit. This is going to be kind of a tangent away from that now. When we talk about distances in space, kilometers don't really have much use, right? Space is huge. You know, we could even talk about like the distance between, like, I don't know, Calgary and Edmonton, several hundred kilometers. In space, we're talking like millions oftentimes. It's insane how big, you know, of distance there are in space, right? So the astronomical unit, I'm tripping over my own tongue here, the astronomical unit, or AU as it's shortened, is used to measure distances just within our own solar system, right? Now, what it's defined as, 1 astronomical unit is the average distance between the center of the Earth to the center of the sun. Now, the reason we say average, just in case you're wondering, is because, of course, planets don't have a circular orbit. They actually have an elliptical orbit. So in other words, kind of more of an oval shape. That's an exaggeration how I drew that, but you get the idea. If you have an oval shape, there's going to be points where when you are orbiting around something, you're closest to that star. You'll also have points where you're furthest away from it. So if we just took the average of all these distances, you would find that that's equal to 1 astronomical unit. So again, the astronomical unit is a distance from the center of the Earth to the center of the sun. So that right there, if we find Earth on this scale, that's about 1 astronomical unit. If you want to convert that to more Earth-based units, we could say that 1 astronomical unit is a mind-numbingly large 150 million kilometers. See, it's a lot easier to say, you know what, 1 AU rather than, 150 million kilometers. That's why they use it, right? If you're interested in the distances from the sun of other planets in our solar system, Mercury, I believe, is about 1/3 of an AU. Venus is like 2/3-ish. I could be off on these numbers, just judging by this here. Mars, this is a little bit misleading here, I think, because I'm pretty sure Mars is about 2 AU. I'll be honest, you guys could just Google it. It's not anything you have to memorize or anything. But after you get between or away from these innermost planets, the terrestrial ones, you get out to Jupiter, we're talking over 5 AU away. And then all the other ones are really spaced out further. When you see the scale here, I want you just to keep in mind that only up until recent, and I should say recent as in like the last 500 years, only up until recent times, we only were aware of Mercury, Venus, Earth, Mars, Jupiter, and Saturn. Uranus and Neptune were discovered much later, and Pluto, although it's not a planet anymore, wasn't discovered until the early 20th century. And you can see why. They're very, very, very far away, right? Uranus is almost 20 astronomical units away, and Neptune is 30 astronomical units away. Just like multiply this 150 million by 20 or multiply it by 30, you can see just how far away these things are. Pluto, even crazier, at almost 40 AU away and much, much tinier than any of the other planets in the solar system. It's a miracle that thing was ever discovered when it was. But yeah, so long story short, the astronomical unit, much nicer number, because then at least you're just sticking between like 0 and 40 more or less, rather than dealing with literally millions of kilometers. The next kind of unit that we'll talk about, there's several others, but these are the only ones we're really going to care about for now. Light year. This is the one that's very well known. Now, light years are used for distances beyond our own solar system, because once you go beyond our solar system, space is very expansive. So even the astronomical unit becomes too small to actually mean anything. So outside our solar system, distances are measured in light years, or just LY to shorten it up, of course. This is the distance that light travels in a full year. Nothing in our universe travels faster than the speed of light. The speed of light is the absolute cap, and that's at 300,000 kilometers per second. In the scale of the universe, even light speed, despite the fact how it's the fastest thing in the universe, light speed is actually still pretty slow. It takes quite a while for it to go anywhere. Over the course of a whole year, if you're going 300,000 kilometers a second, over the course of a whole year, you're looking at about 9.5 trillion kilometers. But here's what's kind of upsetting about this. I'm going to jump to this final point here. Even with this 9.5 trillion kilometers being 1 light year, the nearest star to Earth, other than, of course, our own sun, is a star that's called Proxima Centauri, and it's 4 light years away. 4 times this. That's like, 38 trillion kilometers away. It's insane how long it takes to get to other places, right? If you were to travel at the speed of light, you're not getting to that other star for 4 years. It blows your mind, right? Anyway, just to visualize what a light year really looks like, if you had a string, just a piece of string that was 1 light year long, you could wrap it around the Earth 236 million times. This is a crazy distance, right? But even in the scale of our whole universe, it's still very small. But we have to come up with some other unit like light years to avoid using absolutely stupid numbers like 9.5 trillion kilometers. That just gets out of hand, right? Now, light is, of course, how we see things. This is going to be interesting. Light is generated by something, or it bounces off something, and then the light enters our eyes, where the image is then processed, and of course, our brain makes meaning out of it, right? Since light travels at a finite speed, at 300,000 kilometers per second, that means for faraway stars and galaxies, we're actually looking at what those things were doing years ago. When you look at like things in the sky, whether it's even our own sun or certainly any of the stars in the night sky, you're not seeing what it's doing at the present time, because it takes time for light to get there. Between us and the sun, it takes like 8 minutes or something for the light to get here. So what you're seeing, if you were to glance at the sun, is what the sun was doing 8 minutes ago, right? You're not seeing it as it is now, you're seeing it as it was a few minutes ago. For crazier things, like if we want to talk about distant galaxies, we're talking far, far, far away. The closest galaxy to us is something called the Andromeda Galaxy, and it's 2.5 million light years away. It would take you 2.5 million years to get there if you traveled at the speed of light, the fastest speed in our entire universe. 2.5 million years. It's insane. It's crazy how crazy far away this stuff is, right? So what that means, on another analogy, not just the fact that we really will never get there at 2.5 million years, what that also means is when you look at the Andromeda Galaxy through a telescope, you're not seeing the Andromeda Galaxy as it is today. You are seeing what it was doing 2.5 million years ago. You're literally looking at what was happening in the past. It's because that light takes time to get here. It's similar to the idea as if someone was far away in a field and you see them chop a block of wood and you didn't hear it, but then like a couple seconds later, you hear, oh, chop, right? It's the same kind of idea. It takes time for sound to travel. It also takes time for light to travel. It's just that light takes a lot farther, or a lot faster. Light is a lot faster than sound is what I'm trying to spit out here. Now, even our own sun, like I said, oh, there it is. Yeah, I was right with that number, 8 light minutes away, roughly. So I don't know what would cause this to happen, but theoretically, the sun could just vanish and we just wouldn't know for 8 minutes, because it would still look like it was there, like nothing happened, and we would see it vanish 8 minutes later. As another point, a lot of the stars in our night sky, if they were, let's say many, many light years away, there's a good chance that they might have actually gone supernova, in other words, blown up by now, and we just haven't seen that happen yet, right? Because the light hasn't reached our planet quite yet. Really cool to think about. There's a lot of implications from this, and it's very fascinating the more you think about it. And I would really highly advise, if you have some free time at some point, see if you can find some videos on YouTube about this, talking about the speed of light and stuff. I'm sure there's some you can find outside of just what I'm providing here. Now, what that brings us to is one final image. We talked, of course, about the development of telescopes changing astronomy. In the, I believe, early 1990s, they launched something called the Hubble Space Telescope, which is the most powerful optical telescope in existence. In other words, it's the most powerful telescope that produces visible light images. They stared at a really, really, really small point in space, really, really, really tiny, and they stared at it for days and days, if not even weeks, I believe. And they processed a lot of light that entered this telescope. And when they processed the image, this image formed. Every single little speck and smear that you see on the screen right now is an entire galaxy. But more so than that, a lot of these galaxies are literally billions of light years away. So in other words, what this image is showing is what the universe was doing at different parts billions of years ago. We're seeing the distant past. In a lot of these cases, it's before even our own solar system formed. Fascinating stuff, right? The fact that the speed of light is finite and doesn't actually travel at an infinite speed and gets here immediately, it actually has some really cool implications. It really tells us a lot of information, and it allows us to look into the past for things that are very, very far away. So enough of that. We're going to have a little bit of time for practice. If you don't quite get to these practice questions, today, that is just fine. Tomorrow's lesson, I just have an interesting video. I didn't make the video. It's just a video about the Hubble Space Telescope that I found. It's much shorter than this video was, so you'll have lots of practice time tomorrow. But if you want to get a stab at these questions, there they are on your screen right now. I've also posted the textbook page online for those of you who weren't able to come grab your textbook from school. So these questions are available for you. If you have any questions, please let me know.